Morning, everyone. How are we doing? Questions while we wait? So Danielle is asking, find the 7th and 110th derivatives. There is no way to do that in general. In these questions, they're asking you to see a pattern developing. And that's what needs to be done. Yeah, so you have to do derivatives until you see a pattern, and then generalize to what happens at the 110th derivative. Katerina is asking to post Friday's lecture. It's been posted. It's been posted. What you might not realize when you scroll down to the end, the last lecture available is Wednesday's lecture, but then you have to click on the button on the bottom that says load more or something to that effect, because we have essentially run out of room on the first page. So you're going to load more, and then you'll see it's there. Questions? Anybody? How's the midterm? Too easy? Really? Different indeed. Different indeed. Right, and I mean you understand the issue with the A and B, right? I mean, the thing is, that we need a way so that you're not just using Wolfram alpha and things like that. Well, that's it. I mean, they're just constants. So. Oh, good. Well, that's the thing, right? I mean, you have 72 hours, so you don't have to rush. But at the same time, if you spend a lot of time, then, I mean, it is time consuming. The idea is that, I mean, if you can take the derivative of cosine 2x, then you should have no problem with the derivative of cosine ax. Zoe, if you're talking about question 1, where it asks for f inverse of 0, you didn't have to do long division. Oh, question 9? I don't remember what question 9 was. Exactly. You could factor by grouping in question 1. Right, so I mean, if you can do this, then you can do that and vice versa. actually, Sean is preparing a video where he's going to go through the whole. It might actually even be a video, it might be a live lecture, I'm not sure. But Sean has prepared something that where he'll go through everything. Right, intermediate value theorem. Right. Right, very good. All right. Questions? Right. One was not easy. One you had to see. Yeah, it was. It took me a few seconds to figure that out. Yeah. All right. Very good. So, well, I mean, I don't remember what 9 was, but some people are saying intermediate value theorem. The idea was that you could not solve for x, right? When it was 12 that limit? Yeah, it was tricky. So somebody emailed us with a very interesting approach to that, which was unexpected. Well, I mean, of course, we want the answer for all values of a, right? So, well, exactly, right? I mean, you could factor out a 1 over a, but you'd still be left with and, you know, I mean, maybe as a hint, here's the idea. If you, instead of looking at it in terms of x, what if you called it h instead of x? Can we see where this is headed? If we let f of x be this is really that limit, is really the limit of f of 0 plus h minus f of 0 over h. So it's the definition of the derivative. This is the derivative. It's the derivative at 0. So you know what the derivative is. It's a e to the ax. So it's 1 over a times a e to the 0, which is 1. It was just observing that it was the limit definition of the derivative. Yeah, some people did something different. And I mean, as long as it's, yeah, we'll see. No. If your justification is completely wrong, you don't get any points. Maybe squeeze theorem. I don't know. Maybe. We'll see. But let's not worry about it. But for sure, I think that was one of the difficult questions here. I mean, it's easy once you see it. What is today's lesson? Today we're going to start maximizing. We're going to ask the question, how can calculus help us to figure out the maximum and minimum values of the function? The grading should take at least a week. So let's say early November for the marks. If all goes well, we'll see. Good news. Yeah, some people, Matthew, some people use that as well. We'll see. We'll see. Well, that's the thing, right? I mean, you're not supposed to know that. That's why I wasn't expecting you to use that. Some people in Professor Lumley's class, Professor Lumley actually gave a reformulation of that. So some people did use that, at least one person. So we'll see. Look, let's not worry about it. Yeah, Youssef, I think that's what the other person did as well. Yeah. The good news is that we're nearing the end of the semester, and we're actually pretty far along in the course. So we're running out of material. So what I propose from now on is, instead of doing an hour and a half every lecture, we'll just stick to the 1 hour. We should have plenty of time to finish everything and do some review in the last week or even in the last 2 weeks. Yeah. So, I mean, of course, I'll stick around at 12:30. If you've got questions, we can answer them, but that'll be it for the material. So we'll go from 11:30 to 12:30, and answer questions if there are any. All right, so that's the idea for today. We're going to see how calculus can help us evaluate maximums and minimums. And of course, I mean, these have immediate applications. Think of a business. You want to maximize the profit. Immediate real-world applications right there. So let's start with a definition so that everybody's on the same page. What does it mean to be a maximum? Consider a function f of x with domain D and let C be a number in that domain. F of C is the absolute maximum of F in D if f of x is less than or equal to f of c for all values of x in the domain. Yeah, I think we're now in chapter 4, 4.1. I don't remember what number 14 is. You can ask me at 12:30. Let's just do this material and we can do question 14 afterwards. Consider a function. So, I mean, here we have the definition of absolute maximum. It's exactly what you would expect it to be, right? F of c is the largest f of x gets on the domain. And we can define, I won't do it, but absolute minimum. Similarly, right, where the absolute minimum, the inequality goes the other way. Your function is the smallest it gets. Mr. McGee, I understand. There's no worries. I understand some of you did not realize the question had been updated. We're going to be lenient and accept both answers. There's no worry. Nobody's out to get you. In fact, the original no interval was given. All right, so we have absolute max and absolute min given right here. Now, we're in very much the same way that we usually do here in calculus, we're going to import this idea locally. We're going to import this idea locally. F of c, so, sorry, let me start over. Same conditions before. Consider a function f of x with domain D. And let C be in the domain. F of C is said to be a local maximum if f of x is less than or equal to f of c for all x near c. What does that mean? What does that mean? If there exists an open interval I containing, so an open interval I in the domain, containing C, containing C, and where f of x is less than or equal to f of c for all x in that interval. Local max, exactly that. So long-winded definition, let's illustrate with, first of all, let me go on and say local min similarly. let's illustrate with an example. An example in the form of a graph, which will illustrate the nice difference between absolute and minimum. Where did I lose you here? Maxwell notation. What notation are we talking about? I don't believe I've introduced any new notation here. All I'm saying is the interval is contained. So this is set. This set is contained in that set. This D is the domain here. Well, let's look at the graph. I believe the graph will explain everything. What do we say? You have this function here, y equals f of x. I think it's clear. What is the C for, though? Well, the C is where the function has the local maximum. Right, let's illustrate right here. First of all, I think it's clear that the function never gets smaller than the value it is right here. Right, so that value, which is f of a, this f of a is the absolute minimum. The function never gets smaller than the value it is right here. Similarly, the function never gets larger than this value. So that's the absolute maximum. Right, so absolute min right here, and absolute max right here. However, if you look over here, and if you restrict your attention to points around C, the function never gets smaller than what it is right here in a small interval around C. It does eventually get less if you move far enough away, but locally, your function has a minimum at C. Here we have a local minimum occurring right here. And similarly, let's call it C1, we have a local maximum occurring right here, right? Locally, the function never gets larger than this value right here. If you restrict your attention to a small enough interval, then the function is maximized at C1. Of course, if you allow the interval to get larger, eventually it is surpassed. But if you remain locally near C1, you have a local maximum right here. We want, Matthew, we don't want infinity. We don't want infinity. But as you point out, sometimes you don't have an absolute maximum, right? If you are looking at a function y equals x squared plus 1, this function has an absolute minimum of 1 occurring at 0, but it has no absolute maximum. right? So some functions have an absolute maximum and no absolute min. This function has an absolute min, but no absolute max. And some functions have neither. Some functions have both. Observe that an absolute max is also a local max, right? Because if you restrict your attention in this case to an interval near B, and here, of course, if you are restricting your attention to the interval AB, there's nothing on the right of B. So if you restrict your attention to values in here, of course, you also have the local max. So an absolute max is a local max, but not necessarily vice versa. So we would not say that we have an absolute max of infinity, rather that it does not have one. Exactly that. Right, so these definitions are just describing what's happening here. So it's a long-winded way of saying what an absolute max or local max is. But if you think, now that you know what an absolute max and a local max is, if you try to describe that mathematically, then this is the definition you would come up with. So an absolute max can be a local max, but not necessarily vice versa. That's exactly right. The definition says open interval. Does it have to be open? It does not. It could be closed. What we want to stay away from is just the point. So as long as it's an interval containing more than one point. Right? So I mean, the problem with closed interval is you could have a closed interval like this, C1 to something. C1 to something. In other words, you might not choose any points on the left of C1, and that would lead to issues. An open interval is an interval with round brackets, meaning not including the endpoints. So the reason we restrict our attention to open is because closed intervals with these square brackets could lead to issues if we're not very careful. Theorem. Well, exactly the kind I was suggesting here. If you look at C1, if you take the interval C1 to alpha, the closed interval C1 to alpha, C1 being a left endpoint, that would mean that you're not choosing any points on the left of C1. So this really wouldn't be telling you anything about the graph. Right? It wouldn't tell you what is happening on the left of C1. You want your function to be a local max, but, I mean, if you had something like this, if you just restrict your attention to the left, then yes, all the values are less, but you're not looking at the right. And that's a problem. That might lead you to believe that you have a local max, when in fact you do not. You have to look at both sides. And that's the That's what the open interval allows you to do without saying anything else. Theorem, a continuous function on a closed and bounded interval So this is what a closed and bounded interval is, right? Closed and bounded, where a and b are not infinity, attains an absolute max and an absolute min on that interval. Because of the T and the I, there needs to be a space, right? Is that? I hear you. All right. So continuous function on the closed and bounded interval attains an absolute max and an absolute min. The obvious question that arises, if a function is constant, does this theorem still apply? It does, right? A constant function is continuous, and then the absolute max is actually equal to the absolute min. Very nice observation there. Right, you see what's happening. If you have a function which is constant, it's continuous, and the absolute max is the same as the absolute min, and it's whatever that value is. So this still applies. The obvious question that arises, if a continuous function attains an absolute max and an absolute min, where can these occur? Where do these occur? Valid question. And the answer comes to us via Fermat's theorem. What does Fermat's theorem say? If f of x has a local max or min at x equals c, and the derivative exists, then the derivative must be zero. Well, it's the same guy as Fermat's last theorem, but of course you know that it's not that theorem. I won't prove this now. We will prove it probably on Wednesday. For now, let's just assume it to be fact, right? So what is this saying? If you have a local max or min and the derivative exists, then the derivative has to be zero. L'Hôpital's rule is coming up. If not by the end of this week, then next week. And, right, so if the derivative exists, then the derivative has to be zero at local maximum. This motivates the following definition. a critical number of a function f is a number c in the domain of f, where the derivative is 0 or the derivative does not exist. That's what we're saying, Benjamin. The rate of change at the point C has to be 0 in order for there to be an absolute max or absolute min. Yes, THM means theorem, Fermat's theorem, or this right here. Right, so Fermat's theorem motivates the following. We define a critical number, C, to be a number in the domain where the derivative is 0 or the derivative does not exist. Right? And by Fermat's theorem, the only place you can have a local max and min are at critical numbers. I usually refer to these as critical points. It's actually slightly incorrect. The point itself, right, this is the actual critical point. I usually just refer to that as C. Well, exactly. I'm defining what a critical number is right here. So a critical number is a number C in the domain where the derivative is 0 or the derivative does not exist. What is IVE there, Matthew? Intermediate value theorem. I mean, not quite, right? Because it has to do with the derivative, first of all. And it's not really an intermediate value theorem for the derivative either. There actually is an intermediate value theorem for the derivative. It's called Darboux theorem, which we will not really see, but I mean, it's out there. So critical numbers can only be at local max or absolute maximum. It's actually the other way around, Jennifer, right? The local max and min or absolute max and min can only occur at critical numbers or at the endpoints of the interval. Right, so that's the takeaway from this. And let's take a few examples. We are asked to find the critical points. So let's just start with this. Consider this, find the critical points. So what are the critical points? Well, you start with the derivative. First of all, and you understand, of course, that the domain is all real numbers here. Take the derivative. Derivative is easily seen to be 3b squared minus 12. If we factor out a 3, we have this, and if you factor, this is what we have. This derivative exists everywhere, right? So there is no point where the derivative does not exist. Very well behaved. So critical points, right? Again, I'm using the word critical points. It really should be critical numbers, but I've been using this forever, and I'm too old to change. So critical points are where the derivative is going to be 0. Namely, you tell me, when is the 0? At plus or minus 2. Thank you. And that's it. Plus or minus 2 are the critical numbers here. Same question, different function. Should you find the y value as well? Here's the thing. The critical point itself should include the y value, but here this v, this is really just the critical number. If the book is asking for the critical points, I believe they want the y value as well. I mean, on an exam, it's not going to be an issue. It'll be clear whether you, I mean, normally this is sufficient. What do these critical points actually mean for the function? It's a valid question, right? And look back at Fermat's theorem. These are the points where the function can have a local max or a local min. How can we find which critical point is the max or min? Let's postpone that. We'll do a few examples in a moment. Let's just look for critical points here. What are the critical points? Well, you know what the graph of this looks like, right? First of all, I mean, you know the graph of absolute value of x, and this is just a composition. So, well, I mean, if you graphed y equals 3 minus 2x, you know that it's this, where the x-intercept is 3 over 2. So the absolute value of this, everywhere it's positive, it remains, and everywhere it's negative, you're going to graph it positive instead. So the absolute value this is the graph. And you see that you have this corner occurring at 3 over 2. I mean, you've seen these kinds of examples before. You know that the function is not differentiable. At 3 over 2. Everywhere else, the function is differentiable, right? Because this is going to be 3 minus 2x. for values less than 3 over 2. And otherwise, it's 2x minus 3 for values bigger than 3 over 2. So it's not differentiable at 3 over 2 because of this corner. You can prove it using the definition of the derivative, exactly right. You can prove it using the definition. Everywhere else, the derivative is either going to be negative 2 or positive 2. So the only critical point is 3 over 2. And notice what is happening at 3 over 2. Since we do have the graph here, it's obvious that at 3 over 2 we have anything occurring at 3 over 2? A cusp, a corner, yes, but more importantly in this context, an absolute minimum. Thank you, Matthew. Consider this. Same question. We're looking for absolute maximum. Sorry, not that. We're looking for critical points, just critical points. Take the derivative. First of all, what is the domain here? What values of p can you plug in? Because as you know, critical points have to be in the domain. Domain is all real numbers, right? Because the denominator is never 0 here. Thank you, come on. And let's take the derivative. How do you differentiate? You know what's happening here. Derivative is so the function that is not differentiable doesn't mean it doesn't have a critical point. We have to be in the domain. We have to be in the domain. The derivative quotient rule, as suggested, v u prime minus u v prime all over v squared. What is that? That is a minus 2p squared plus p squared. We get a minus p squared plus 4 plus 2p. Is that correct? Or if you factor out a negative, you get p squared minus 2p minus 4. Which factors does it? Might not factor. We're having trouble factoring. Is that correct? We're having trouble factoring. First of all, what are the critical points here? You've got a fraction, so you know if the denominator is 0, the derivative does not exist, but there are no points where the denominator is 0. If the numerator is 0, the derivative will be 0, so we search for when this is equal to 0. We couldn't factor it nicely. We search for the roots using the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. And this is going to be 2 plus or minus 2 root 5 over 2, or 1 plus or minus root 5. And that's why we That's why we couldn't find them. Those are the critical points. 1 plus or minus root 5. Why did we only solve for p in the numerator? That's because we knew the denominator was always bigger than 0, right? In fact, the denominator was always bigger than or equal to 4. This p squared is something positive. So 4 plus anything positive is never going to be 0. Exactly that. So here's your h. Before we attempt anything, let's discuss the domain here. What is the domain? You know what it is. Domain. Everything except 0. All real numbers except 0, right? Because of the negative exponent here. Let's take the derivative. Whatever you want to do, right? I mean, here you could have expanded this and differentiated each piece separately, or as it's written, it's a product, so product rule applies. Let's do that since and now this is where simplification becomes of crucial importance, right? You're figuring out where the derivative is 0 or where the derivative does not exist. You need the simplest form of the derivative. Let's factor out the smallest power of x. Here you have x to the negative 4/3. Here you have x to the negative 1/3. We're going to factor out an x to the negative 4/3. The smallest power present in both. Let me throw in the negative 1/3. The midterm didn't ask you to simplify only because it's easier to mark when things aren't simplified. But you understand now that simplification is going to be very important here. If I factor that out, I factor this whole thing out, I'm left with an x minus 2. And I factored out a negative 1/3, so I'm going to need a minus 3 to compensate. Right, negative 1/3 times negative 3 gives me the 1 that I had here. And I had x to the minus 1/3. I factored out an x to the minus 4/3. What am I left with? I'm left with what power of x? I claim it's x to the 1. Let's convince ourselves. For those of you not convinced, this minus 3 times minus 1/3 gives me a plus 1. X to the minus 4/3 times x to the 1, you know that the exponents add. Minus 4/3 plus 1 is the minus 1/3. Why did I factor out a minus 1/3? For simplicity, I could have left it in, But it's going, as Kayla suggests, it's going to be easier to work without fractions, right? What do I have now? Minus 1/3 next to the minus 4/3, and this is minus 2 minus 2x. Or if you factor out a minus 2, you get a 1 plus x. And now it's trivial. Now you can just read off what the critical points are. What are the critical points? Critical points are where the derivative is 0 or where the derivative does not exist. Derivative is 0 if x is minus 1. And the derivative does not exist if x is 0. But 0 is not in the domain. So, by definition, 0 is not a critical point. For all intents and purposes, you'll see that we have to treat it as if it was, but it's not a critical point. Because again, critical points have to be in the domain. Because when we say, so Benjamin is asking why is it more correct to say critical numbers rather than critical points? When we talk about a point, we mean a point xy versus the number x. So critical points actually should include the y coordinate as well. But I like to confuse the two, and nobody's confused. But per se, when the book asks for critical points, they actually mean the xy point versus the critical number, which would have been -1 here. Consider the following scenario. We want to maximize this function on this interval. Well, it's a continuous function, right? It's a polynomial. You know, it's well-behaved, continuous, differentiable, blah, blah, blah. On a closed and bounded interval, it has to attain an absolute max and an absolute min. Where can these occur? At critical points or at the endpoints. So let's find the critical points by taking the derivative. The derivative is 54 minus 6x squared. If we factor out a 6, that is 9 minus x squared, which factors nicely. That's 3 minus x. 3 plus x. Differentiable everywhere. Since it's closed and bounded, no, we don't treat it any differently. Not for now. Not immediately. We still search for the critical points. And what are the critical points? Right? Critical points are where the derivative is 0 or the derivative does not exist. We have 3 and -3, but as Michael points out, Negative 3 is not in the domain. Right? Negative 3 is not in the domain. We have to restrict our attention to the domain here. So what? Critical point is 3, and what we noticed earlier is that the absolute max and absolute min must occur either at critical points or at the endpoints. So look at your function at the critical points and at the endpoints. Largest value is going to be the absolute max. Smallest value is going to be the absolute min, and that's it. F of 0 is easily seen to be 5. F of 4, I don't know what that is. That's 8 times 16. Is that 93? I want to say 93. Thank you. Thank you. And F of 3. 54 times 2. 108. 113. 113, anyone? Is that right? Can anybody verify that? Thank you. And there it is. So this is the max, and this is the min. Do we have time for one more? Let's do one more. We'll call it a day. Well, these are in fact absolute. Right? We have a function, continuous function on a closed and bounded interval. We know it attains an absolute max and an absolute min. Consider this. First, let's talk about the domain here. When is the denominator 0? And if you apply the quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2a, we see that it never is. So the function has domain all real numbers, right? The denominator is never 0. So this being a rational function, rational functions are continuous on their domain. The denominator is never 0. So this rational function is continuous everywhere. How would the answer change if the brackets were round? Well, I mean, let's look at this example. If the brackets were round, 0 would not have been included. So you actually would not have had an absolute minimum. Right? 0 and 4 would not have been included. In this case, the absolute max occurred somewhere in between, so there's no issue. But we have a theorem that tells us that continuous functions have an absolute max and min on a closed and bounded interval. no guarantees if the interval is not closed. So if it's an open interval, may or may not have max or min. Let's finish that up by finding the derivative. Vu prime minus uv prime all over v squared. Simplify the numerator, minus x squared. This is plus x, which cancels with that. And you know the denominator is never 0. So you know that the only critical points are going to come from the numerator and when is the numerator equal to 0? It's equal to 0 when x is 1 or negative 1. But looking back at your domain, negative 1 is not included. Right, so the only critical point is 1. And as before, all we need to do is look at the function at 0, 1, and 3, at your critical points and at your endpoints. Whichever one is largest is going to be the absolute max. Whichever one is smallest is the absolute min. Don't mistake plugging it into this, right? It's not the derivative we're looking at, but the original function itself. So when x is 0 in here, the function is 0. When x is 1, you get 1 over 0 plus 1. And when x is 3, 9 minus 3 is 6, plus 1 is 7, 3 over 7. And there it is. Absolute min, absolute max. Maxwell, how would the answer change if the brackets were round? Well, if the brackets were round, 0 would not be included. So you would actually not have an absolute minimum here. F of 0 is not undefined, right? If x is 0, the denominator is 1. In fact, we saw that the denominator was never 0. But there wouldn't be any testing. That's the thing. If the brackets were round, what I would suggest is close them. Close them, include the endpoints that are not included, determine what happens there, and then fix it. So in this case, if 0 and 3 were not included, I would have included them. This would have been the answer for the closed case. And for the open, what would you conclude? You would conclude still an absolute max occurring at 1, but no absolute min, because the function can get as close as you want to 0. Well, absolute gives us more information, Annie. And he was asking, why is it absolute max and min as opposed to local max and min? Absolute gives us more information. And how are we doing? We're back? Buffering still? Back. Very good. Very good. So, but I mean, you know, that's it. That's it. We said we were going to start ending early. Questions? Practice this Idea of critical points, max and min. Did somebody have a question about the midterm? I think we were going to discuss that. Was it Michael or somebody else? No? Anything? I'll wait a moment in case. Any questions? Anybody? That's it? Catherine is asking if the interval is open and you only have one critical point, how do you know if it's an absolute max or an absolute min? It could be neither. It could be neither. We don't know. We don't have enough information then. So more analysis would be required. And yeah, we'll see how to answer that in the weeks to come. No more new material. Some people have questions about the midterm. We can address those now. Number one, remind me what number one was. I want to say I want to say this. I want to say that for number one, and the idea was to observe that if you factor out an x squared from this part to ax minus b, you get that, which is x squared plus 1 times 2ax minus b. So x equals b over 2a is a root. In other words, f of b over 2a is equal to 0. So f inverse of 0 is b over 2a. Tell me what 14 was. X minus h squared plus y minus k squared is equal to r squared. And what was the question? Find the tangent. So you could do implicit differentiation. Nothing wrong with that. Yeah, absolutely. That's fine. Or you could actually solve for y equals a function of x explicitly. Either way, both will. Yeah. It's all good. Very nice. Very good. But you never square root a negative, right? Well, I mean, you have options. So either you isolate y, or you don't. Either way, whatever you want to do. So I mean, you've got options here. Whatever you want to do, and it's all good. the derivative of a to the b to the x. Well, you know what that is. This is a to the something. So the derivative is a to the something, ln a, times the derivative of the inside. The inside is b to the something, whose derivative is b to the x ln b, and that's it. All right. Questions? Well, Michael, as long as you justified everything, if that's the right answer, I don't know that it is, but the important thing is to justify. Can you work out 14b, please? What was 14b? It was this. Asking for what now? So if we differentiate the whole equation with respect to x, let's do it using implicit differentiation. So 2x minus h plus 2y minus k dy dx is equal to 0. And so dy dx is easily seen to be, bring this to the other side, there you go. And if you plug this in at the point AB, then this is going to be minus a minus h over b minus k. This is as long as, well, there's as long as b minus k is not 0. Well, I mean, if you're doing it not with implicit differentiation, the answer is going to be different. It's going to look different, but it's going to be equivalent. So I'm going to let you determine what it is in that case. So the slope at AB is going to be this. As long as B is not equal to K, in that case, if B is equal to K, we have a vertical asymptote. I mean, a vertical tangent line. What is 2a? Give me 2a and then we'll end with that. Like I said, Sean is putting something together. So, well, give me those questions quickly. I don't know what 2a and 5a are. Anybody? 2A, 5A? What is that question asking? No. Domain and range. Very well. This is e to the ax minus b like that, all over e to the ax plus b. Domain and range, and what were there any conditions on A and B? No conditions on A and B, I assume. All right, well, if b is bigger than 0, you know the exponential is always bigger than 0. Both must be positive constants. Very well. Very well. So since the exponential is always bigger than 0, you know the graph, then the denominator is always bigger than 0 as well. Right? In fact, it's bigger than or equal to b, which is bigger than 0. So, conclusion. Domain is all real numbers. That's it. And as was pointed out, if you're looking for the range, that's always a bit harder to answer. But if you can solve for the inverse, you can just talk about the domain of the inverse. It's going to be the range of this. Exactly that. Exactly that. And that's the easier way to go. So if you found the expression for f inverse, you ask the question, what's the domain there? It's all good. All right. Okay. Why don't we solve for it quickly? You know how to solve for the inverse. You interchange x and y. For the original one, it didn't say if A and B are all real numbers. Well, I mean, if apparently people are telling me that this was added in. If it wasn't, then you would, I mean, right? You would have to determine what happens if B is right. So it, you know, I mean, originally it wasn't there, and that's what was approved. And then you had to determine if B was bigger than or equal to 0, you're good to go. Domain is all real numbers. If B is not equal to 0, if B is less than 0, then this could be equal to 0. Where is it equal to 0? It's equal to 0 it's equal to 0 at ln of negative b over a. So in that case, the domain would have been all real numbers except ln of negative b over a. So if it doesn't say that b is positive, which it didn't in the beginning, and that's how it should have remained, that's how it differs. If b is positive, all real numbers. If b is negative, all real numbers except that. We were solving for the inverse. Let's finish it up for completeness. Bring that to the other side. X e to the ay plus bx e to the ay minus b. Bring this to the other side. X minus 1 e to the ay. And bring that over. Minus bx minus b. Divide. Take the ln. And divide by a. Maybe I'll factor out a minus b here. X plus 1 over x minus 1. There you go. So now if you're looking for the range of the original, it's the domain of this one. And what is the domain? Domain of f inverse? Well, you're taking ln, so this stuff better be positive. You can get part marks. I don't know how much these are worth, but if it's a 1 mark question, I mean, don't expect a 0.5 or anything. So it's either going to be 1 or 0. That's why originally the exam was out of 30 marks. I made some questions worth more so that we could give part marks. But yeah. So you understand what's happening here, right? We certainly don't want x to be 1, because that would give you a 0 in the denominator. So x equals 1 is out. And you know you can only take ln of a positive number. So this stuff, this fraction here, has to be negative. No, and in fact, it cannot be 0. It cannot be 0, so you cannot have x equals negative 1 either. And you need this thing to be less than 0. So now solve for that. When is this less than 0? So if x minus 1 is bigger than 0, multiply both sides by x minus 1, the inequality remains. So you get x plus 1 is less than 0, so x is less than negative 1. So if x is bigger than 1, then x is less than negative 1, and here you don't get anything. There are no values that are simultaneously bigger than 1 and less than negative 1. And if x minus 1 is less than 0, then multiply this whole thing by x minus 1. Since it's negative, the inequality reverses, and you get x plus 1 bigger than 1. So here, this is x less than 1. If x is less than 1, sorry, this is 0. X plus 1 has to be bigger than 0. So x has to be bigger than minus 1. If x is less than 1, x has to be bigger than minus 1. And so you get between negative 1 and 1. Beautiful. There it is. That's actually the range of the original function. How are we doing here? You probably could have proven this using an inequality as well, right? The original function was e to the ax minus b over e to the ax plus b. You can probably squeeze this. Well, in fact, you absolutely have to be able to do that. You can probably squeeze this between negative 1 and 1. I actually have to go. I'm already late. So we'll call this a day. We'll pick this up again on Wednesday. We can go over 7a at that point, at that time, if you wish. Thank you all for coming, folks. I will see you on Wednesday.